There is another point of attention, which is that we need the norm of AH multiplied by the norm of the inverse of AH to be as small as possible. And that is called kappa. This is called the condition number. And somehow it measures the sensitivity of the solution UH to small errors on the right-hand side on BH. And let me give you an example here. Basically, if you, let me actually just do this here. Okay, let me just give you an example. It's just easier to understand on an example. So I'm importing NumPy in Python, and I'm currently defining here a matrix A. So here is my matrix A that I'm typing in. And so here is the matrix. Print A. I can make a mistake here. Okay, well, here's the matrix. And then I'm going to enter a vector. So here's the vector B. And what I'm going to do is, well, print B. And what I'm going to do is to solve AX equals B, right? So, well, it's not very difficult to solve, by the way. I mean, obviously, considering A and B. Even before we actually type the print X, we can actually figure out what is the solution. So X, obviously, is pretty easy, isn't it? Okay. But now, let me actually change B. I'm going to change B into another B, right? Okay, so I'm taking my B, and I'm just changing it slightly. It's a very, very small change, as you can see. And let me compute the solution again. Is the solution close to the previous solution? Well, let's print it. Not exactly close, is it? So you see, a small variation in B will provide a not so small variation in X. And this is due to the fact that if you compute the norm of A, and you multiply it by the norm of A inverse, then you actually have a pretty big number. That is a condition number. And obviously, you do not want this with your rigidity matrix. That would be a problem. Walking down memory lane today. So let's understand what happened. How come such a small variation on B gave us such a large variation on the solution X? To understand this, I will introduce the condition number. Let me define it. First, I'm going to consider a norm on RQ or CQ. Let's just consider RQ to simplify things. So that norm with 2 bars is the norm that I'm going to consider on RQ. It can be the norm infinity, it can be the norm 1, it can be the norm 2, just a norm. Now, I will consider a norm with 3 bars on the space of matrices. That will be the induced norm that we just defined in the first video of this section. Now, if I consider a non-singular matrix A, I will define the condition number of A as the product of the norm of A multiplied by the norm of its inverse. And that will be denoted kappa of A, and again called the condition number of the matrix A. Let's see what is the condition number on the matrix A we just saw in the flashback. So first I need to define a norm on R2. I could take the norm infinity, I could take the norm 1. I will choose the norm 2. Now the matrix I consider was 4.1, 2.8, 9.7, and 6.6. Let me compute the norm 2 of this matrix. Now, as you know, to compute the norm 2, I need to look at the eigenvalues of A transpose A. So, well, basically, I'm going to multiply A by A transpose, A transpose by A. Then I'm going to compute the eigenvalues. You can just verify that no mistake was made. And we find lambda 1 and lambda 2. The largest eigenvalue will be lambda 2, and therefore, the norm of A will be the square root of lambda 2, which is the number right over there. Now, of course, I can approximate lambda 1 and lambda 2. Lambda 1 is actually pretty small, and lambda 2 is about 162. So the square root of 162 is, roughly speaking, 12.7. Here is going to be the norm of A. The norm, of course, subordinated to norm 2 of R2. Then I can, I can compute the norm of the inverse. So I'm going to compute A inverse transpose multiplied by A inverse. I'm going to compute both eigenvalues. I'm going to the largest one, that's mu2, and therefore the norm of A inverse is going to be the square root of mu2. Let me actually just give you some approximations of these values. Well, roughly speaking, the norm of A inverse will be 127.4. So what I'm saying is that the condition number will be 1618 roughly. Okay. Now here is a proposition. If I take a matrix, which is not singular, and I take B1 and B2, two vectors in RQ, and we'll choose B1 and B2 not to be equal to 0, and x1 and x2, that will be the solution to the system ax equal b, then what I'm stating is that the error, the relative error on the solution will be bounded by the condition number multiplied by the relative error on the right-hand side. Okay. Where the condition number is computed with the norm of the matrix that is, induced by the norm which appears here in the formula. Okay, let me actually explain to you why this is so, and then we'll see what it means for the example that we just discussed. So let me prove this inequality. Actually, it's very easy to prove. What I'm saying is that if you look at x2 minus x1 divided by x1, which hopefully is not 0, then simply x2 can be written as A inverse b2, and x1 can be written as A inverse b1. In other words, the norm of x2 minus x1 is simply the norm of A inverse implied to b2 minus b1, which obviously will be smaller than the norm of the matrix A inverse multiplied by the norm b2 minus b1. Now, if you look at what you have for 1 over x1, over the norm of x1, well, since b1 is ax1, then b1 will be smaller than the norm of A multiplied by the norm of x1, which means that 1 over the norm of x1 will be bounded above by the norm of A divided by the norm of B1. So if I plug this in back to over here, what I get is the norm of A inverse times the norm of A multiplied by B2 minus B1, the norm of B2 minus B1, divided by B1. In other words, you get exactly the inequality that you get here, since kappa is the norm of A inverse multiplied by the norm of A. All right, so what it means is that if you look at the way an error on the right-hand side on B will impact an error on the solution, well, basically the error will be multiplied by the condition number. So if the condition number is large, well, you're going to amplify a lot your error. That's what you're saying. So if you look at the matrix from the previous example, the one that we just with the flashback we had, then remember we changed the right-hand side by only 0.1, which seemed very small. But as you can see, that error, that's change, could potentially be amplified by a factor of 1618. So that can lead to a relative variation of 161.8 on the solution. So what we're saying is that the condition number first is always going to be greater than 1, right? I mean, obviously the norm of A multiplied by the norm of A inverse, that's always greater than 1. But the best case scenario, of course, it's 1. But if it is really large, then it is potentially a problem. In other words, when you solve a linear system, if your condition number is not small, is not close to 1, then potentially you will have a large variation on your solution when you have a small variation on your right-hand side B. And you see why this can be a problem when you solve, when you approximate the solution to a PDE. When you try to find the approximation of the solution to a PDE and you use the finite element method or the finite difference method, then the right-hand side will be computed, but you will have numerical errors, you will have, you can have all sorts of errors. If your condition number is really large, these errors will propagate to the solution and will be amplified by this condition number. So you really want the condition number to be as close as 1 as possible. Now, if you have a matrix A, you have a matrix A. I mean, it's not like you really have a choice. A lot of people would say, okay, well, I would like to have a small condition number, but what if I don't have a small condition number? Well, in this case, often you use what is called a preconditioner. So what you do is, instead of actually working with A, you're going to work with P times A, and then eventually you will just recover your solution because you know by what you multiplied. So, instead of working with A, you work with PA, and hopefully PA will have a condition number that will be smaller than A. So that is called preconditioning, and that helps your approximation, your numerical simulation. Now, of course, if you have a non-singular matrix, the best possible preconditioner is going to be the inverse of A. I mean, that's the best preconditioner you can get because A inverse times A is the identity. I'm sure that the condition number for the identity is 1. But of course, if you know what is the inverse of A, then there is not really a point in solving your linear system to begin with, right? You just apply A inverse to B. So you don't know what A inverse is, and that, of course, is a problem. So what you may have to do, or what you want to do often, is to try to find a P which is easy enough to compute and for which you can somehow get the condition number of PA to be smaller than the condition number of A. So that is called preconditioning, and that is often something that will appear when you are doing the numerical method to find the approximation of the solutions to a PDE. Let me finish this video by mentioning that if you have a matrix A which is a positive definite symmetric matrix, and the eigenvalues are ordered by lambda 1 is the smallest one and lambda q is the largest one, then the condition number kappa 2, which is relative to the matrix norm induced by the Euclidean norm, is given by the ratio lambda q over lambda 1. And I'll let you think about the proof of this proposition, but you can see that it's very useful if your matrix is definite positive and symmetric, and if you know the eigenvalues of this matrix.